Now we arrived at our sheet number 3.3, which is about linear maps and matrices throughout. So the question is, what do we have to consider? First of all, this was a little mistake. I put a one sign here, which is not necessary because it's just this one little exercise. And what is it about? Well, firstly, it's about matrix multiplication, which you have learned meanwhile. And I want to show you also, take this as a little training for multiplying matrices. No, not really, matrices with vectors. But as you know, meanwhile, our usual column vectors are nothing else than special matrices, which have, by chance now, at least in the 3D vector space, they just have 3 rows and only 1 column. So that's what makes them special. But they are matrices much the same way as, for example, this matrix A with 2 rows and 3 columns is a as we say, a 2 times 3 matrix. So this is a 3 times 1 matrix. It works fine. Now, this is the theorem of linearity about applying matrices to vectors. That's what it's about. And if you look at this expression, you can see what it means if a map is linear. Actually, it means what's put here in general form. If you apply the matrix to a linear combination of vectors, and then you can show that the result is the same as if you scale afterwards and then also apply the matrix to all these vectors step by step, to all these single vectors, and then build the vectorial sum of the, like these are the pre-images, you could say. These vectors are the pre-images, and the images are, in this case, I built separately. I built all the images of these vectors, and then I add the images in the image space. While here I would add the pre-images first, in vectorial manner, of course, and then apply the matrix only once to the whole sum of pre-images. And you see that this is something different here and here. But if it leads to the same result, this is a proof that the whole operation is linear. That's all. That's all it's about. And you may see, for your convenience, I just did not use any scaling factors in this example. And this is just a little exercise to see how to do it and to show that the result is the same both ways without any scaling vectors, but by using this method of adding either the pre-images or the images. You will see, okay? So what do? We take this matrix, and now it's important. I should shortly jump here, because now we use a principle which I invented a new, well, you could say, I don't even know how you say in English. In German, it's called Eselsbrücke, Merkhilfe. It's something like to remember, okay, a help, remembrance help for how to do things. And I call it ERTEC. That's what I invented. ERTEC means every row times every column. And that's the principle of vector multiplication. It's all you need to know. You combine every row of the left. Look at this example. Here we have 2 matrices which have to be multiplied with each other. And so you take a row of the left one and combine it with a column. I would say row, I mean row. You take a row here and a column here, and then you combine them, which means you build like a scalar product. Okay, so this number times this number plus this number times this number. This is what I call first row times first column. And this, you see, if I'll just look what I'm doing. If I take the first row and the first column, this corresponds to the element B1, 1 in the resulting matrix. It's quite simple to remember. For example, if I use the second row here and the second column here, I have my element 2, 2, which is this one, okay, in position 2, 2. Second row, second column, second row, second column. So that's really a simple principle which works fine. And actually, I'm doing quite the same here, because even though, even though we have vectors now, as I told you, they are also special forms of matrices, so let's just do it. Now, the left side of this equation tells us we can and we should add the add the pre-images. So we first build the vector sum of the two input vectors, right? And so I do it, and then 1 minus 1 equals 0, minus 3 plus 1 equals minus 2, 2 plus 0 equals 0, 2 plus 0 equals 2. And this means after I build this, the sum of pre-images, I only have one pre-image, which has to be mapped to the image space. By the way, in this way, this is a so-called projection. This kind of rectangular matrix has the property that it reduces the number of dimensions. There are many very interesting applications. For example, this could be used to build a two-dimensional projection of a three-dimensional space. Like if you have a perspective view, if you make a photograph, okay, of a landscape, and then what you receive on your photograph, which is two-dimensional, is the result of such a matrix operation. So this is very important in computer graphics and things like that, okay? Because so you don't wonder, or you don't that you get only a two-component vector as a result. Anyway, now I apply this matrix. We also say applying a matrix, which means multiply, to this pre-image vector, like Vertex, okay, every row times every column. I take the first row times the first column, which is 1 times 0 plus 2 times minus 2 plus 3 times 2. Or in other words, 0 plus minus 4 plus 6, which is 2 in the end, okay? Now I proceed to the second row and combine it still with the first column because I only have one column. So that's all I can combine. And this time I get minus 2 times 0 plus 0 times minus 2 plus 1 times 2. 1 times 2 is the only term that remains, which is 2 again. So the result is the vector 2, 2. This is the image vector. By the way, this works fine only if the length of these rows is exactly the same as the height of these columns. So that means if I have a 2 times 3 matrix here and a 3 times 1 matrix here, then it works. In other words, if these inner numbers are the same, okay? If they are the same, the result is, you can read it here, you can extract this number and this number, it means 2 times 1. Sorry, is that 2? Here, that's a mistake. It should be 2 times 1. So the result is a 2 times 1 matrix, which is exactly speaking a column vector consisting of 2 rows, so a 2D vector. So that's fine procedure. And we made it, okay? I used the Vertex principle. And now I do the same by, differently, by adding the images. So this time I apply my matrix to vector A first and then separately to vector B. And only afterwards I add the images. Okay, so this row times first column. 1 times 1 plus 2 times minus 3 plus 3 times 2, which is 1 minus 6 plus 6. So it's equal to 1. You see, I'm here. And so you see that I just calculate the direct image of this vector A, which is also a two-dimensional vector, but a different one than this from before, okay? Now, second row, first column, minus 2 times 1, plus 0 times minus 3, plus 1 times 2. So this is minus 2 plus 2, which is 0. And I'm done. So the next step is here. First row, first column. Minus 1, I multiply, okay? Minus 1, and then I add up. Plus 2 is 1, and that's it. 3 times 0. So that's 1, okay? And then second row, first column. Minus 2 times minus 1 is 2. 0, 0. So it stays 2. Compare these two vectors with this one. They are different, but the sum of these, the sum of the images is 1 plus 1 is 2. 0 plus 2 is 2. And now we have proved, if you want, that in this example, the linearity of this whole mapping is fulfilled. So that was rather simple, but I think it's nice to bring things into play and to understand how to do it, to multiply matrices with vectors. Okay.